Hello everyone. Next video, I'm going to talk about the last part of the oscillation. Okay. It's called force oscillation. Force oscillation. Okay. Previously, we have used the simple harmonic oscillation, right? At the very beginning, simple harmonic oscillation. Where is it? Yeah, simple harmonic oscillation. Look at this. Uh, Simple harmonic oscillation. And after the simple harmonic oscillation, okay, we go to the damp oscillation. Okay, damp oscillation. I think I didn't show the animation, right? Oh, okay. Oh, here. And then we go to the damp oscillation. Oh, sorry. Then we go to the damp oscillation. We analyze the damp oscillation and classify three kinds of damp oscillation, right? Okay, so this damp oscillation, and now the final part is called force oscillation. Okay, and there's a very good video to introduce the force oscillation, but in this video, I'm not going to, to show this video, so you can view it by yourself. And the force oscillation, that's we force the system to oscillate. We force the system to oscillate. Okay, in simple harmonic oscillation, the system always doing the oscillation and never stop. And then we introduce damp oscillation. That means the oscillation will gradually decrease. Okay, gradually decrease. And now force oscillation is we apply an oscillation force. We apply an oscillation force to the system, but your system still have the elastic force and damp force. Okay, the damp force still there. Yeah, actually, in a very in in real system, the damp force is always in your system. It will dissipate energy. Okay, not every system is very ideal, never dissipate energy. Every system always you have something to dissipate or input energy. So the damp force is still there, and also we have elastic force. And now the only difference is we add a apply oscillation force, and this force is also oscillating. We apply the oscillating force. Okay, oscillation force, not a constant force, oscillating force. So the oscillating force is described by the cosine functions, and this is the magnitude of your applied force and times the cosine function. So we are applying oscillating force into your system. Okay, not a constant force. Be careful. We are oscillating. We are applying oscillating force in your system. Okay, so this is the equation of for motion, equation of motion of force oscillation. Yeah, apply a Newton's second law. Okay, summation F as a force, the net force equal to ma. And yeah, we will reach a very complicated differential equation. So complicated differential equation like this. Okay, so first of all, in this video, I still have to explain where this result comes from. Where this result comes from. Okay, I still have to explain a little about this. I think for most general physics textbook, you just ignore this part. But I think that the textbook doesn't want to scare you, so that's why they ignore this part. But I think you still have to know where this formula comes from. Okay, so that's okay. So in the test, I won't test any derivation of this formula, but you still need to understand the derivation process. So, and the derivation process is kind of very long, so I just write it in advance. Okay, so but before we still do a little review. Okay, in simple harmonic oscillation, yeah, that's the equation of motion for simple harmonic oscillation, and we can assume the solution of x is equal to amplitude times cosine omega t plus phi. And omega square is in simple harmonic oscillation. Don't forget, in simple harmonic oscillation, our omega in simple harmonic oscillation, I make sure I should put here. In simple harmonic oscillation, our omega square is k over m. Yeah, omega square is k over m. That's in simple harmonic oscillation. Okay, and then we move to damp oscillation, right? Damp oscillation, yeah, there's a one more damp force term, and we can assume the solution of the damp oscillation is exponential decay function times the oscillating function. And we solve this equation before and not solve. We guess this solution and find out what's the term in the exponential function. Okay, and in the exponential function is exponential minus t over 2 tau, and tau is b over m, and tau in previous content tau is called relaxation time. Sorry, this is wrong. Sorry. Just yeah, lots of formula, easy to 1 over tau. Okay, this is reciprocal of relaxation time. Tau we call it a relaxation time, and the relaxation time is controlled by parameter b. You have large b, that means large damp force. You have short relaxation time. That means you only need a very short time to damp the oscillation. And mass of the system, we just most of the time we just don't tune the mass, we tune the parameter b. Okay, that's damp oscillation. Damp oscillation, equation of motion of damp oscillation, and that's a solution looks like. And in damp oscillation, the angular frequency is not the natural frequency anymore. Okay, in the damp oscillation, we call k over m is the natural frequency. Okay, k over m is natural frequency square. Okay, it's called natural. Omega zero is called natural frequency. Natural frequency square is equal to k over m. Okay, that's a bit difference. So you got to be careful for the terminology. So in a damp oscillation, the angular frequency is no longer the natural frequency anymore. It slightly is the angular frequency. Damp oscillation is a little smaller than natural frequency. Also, it controlled by parameter b. Okay, so you see in damp oscillation, b control lots of things. Damp parameter. And that's why you can tuning your system by tuning the parameter b. Okay, so that's damp oscillation, and now we reach the force oscillation. Okay, in force oscillation, and the force oscillation in the differential equation is much harder to solve. But actually, when you learn engineering mathematics in your second year, I think this is very easy to solve. Okay, after you learn the engineering mathematics, but right now you don't have that capability to solve this this differential equation. So I now just like the in previous two cases, okay, that we can guess the solution, what the solution looks like. Okay, and in fact, in this solution, the solution of this equation of motion has two parts. You can xh plus hp. Okay, and xh is called homogeneous solution in mathematics. It's called homogeneous solution, but you want to add the physical meaning of homogeneous solution, it's called transient solution. Okay, and xp in mathematics is called particular solution. But if you want to add physical meaning on that, it's called long-term solution. In this calculation, we only care about a long-term solution. Okay, we only care about this long-term solution. We don't care about transient solution. Okay, transient solution means it will disappear after certain period of time. It will disappear. It will disappear after some times, and then after that, you only have long-term solution preserved in your system. So that's why we care more about this particular solution or so-called long-term solution. And we can guess the format of the long-term solution. And this is a linear system. Yeah, it's also a mathematical term. This is called linear system. Linear system. This force oscillation is linear system. Okay, linear system. In linear system, your solution is very like your input. Okay, this is input. Okay, this is input. Is the input of your system, and x, actually you can see x is like output of your system. Okay, in linear system your output is very similar to your input. Okay, so our input is a cosine function, so our output, it must be sine or cosine function. Okay, and for this problem, we just assume it's a sine function, a sine function, and and omega, and we put the omega t minus phi into a sine function. And you might ask why not assume it's cosine? Okay, you can also assume cosine, but if you assume it's a sine, the mathematical derivation is much easier. Okay, if you just assume it's cosine, that doesn't change that doesn't change the overall result. But using sine, assume the solution is sine, it's much easier to do the derivation. Okay, and we just like we did in the damp oscillation, once we guess the solution, okay, we put this back into the differential equation and solve this a out and solve this omega out. Okay, our purpose right now is find the a and omega. A and I think it's find omega. Hmm. Do you need to find omega? Let me see. Oh no, omega is the applied frequency. We don't need to find omega. Oh, so right now our purpose is find phi. Okay, phi is phase constant. Assume the solution is like this and find a phase constant. And be careful. This is omega right now is applied frequency. Applied frequency. And we just assume our solution has the same frequency with the input. Okay, this is omega is applied frequency. Okay, we assume our solution has the same frequency as input. Okay, that's the feature of the linear system. Yeah, the solution of linear system is very similar to your input. Okay, but you will learn this in engineering mathematics. Okay. Okay, it's a linear system. Your output were very similar to input. So your input right now is applied frequency is omega. Okay, and your solution or response of the system must be very also have the same frequency, but have the same frequency with the as the applied frequency. Okay, so this omega is given. This is a given. This is a given. Okay. In this problem, this is given. You are given a applied frequency. Okay. Okay. Once we have this solution, so we are this get solution form, we put the switch back into the differential equation, and you need to do the first derivative and second derivative. Yeah. And sine cosine functions, first derivative, second derivative. I assume you already know this. Okay. And you have the first derivative and second derivative. So plug all this information, dx dt, d squared, x dt squared. And here we have to also do the expansion of this cosine function and sine function. Yeah, don't forget this. This is a trigonometric expansion, right? If you forget, let me write the slow notes for you. Okay, if it's, let's say, if it's cosine a plus minus b is equal to cosine is okay, cosine a cosine b minus plus sine a sine b. Okay, do you remember that? And if it's sine a plus minus b, it's sine cosine plus minus cosine sine. And remember that is a basic trigonometric algebra. Okay, just apply these two. Yeah, to expand this sine and cosine function. And okay, and don't forget our initial assumption of the solution. Yeah, this also can be expanded. Omega t minus phi is equal to sine omega t cosine phi minus cosine omega t sine phi. Okay, so you lumped this all information back to in your equation. Yeah, it's very long. It's very long. Yeah, I know. But after all, the left hand side, yeah, lots of stuff you have to add into your system, add into this equation. And after all, you will become blah 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 times the sine omega t plus blah 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 times cosine omega t and equal to f0 over m times omega t. Okay, so that's what's in there. What's in front of sine omega t? Let's see. Okay, don't forget this. When you plug everything in your system. Okay, so you have times the b over m here and times the b over m here, and x is k over m here, so this also a k over m here, so this will have the k over m here. Okay, what do we have in sine omega t? What do we have in sine omega t here? What do we have in sine omega t? So first of all, sine omega t is here. So we have first term minus, do we change the color? Do we change the color? Do we change the color? Okay, let's change the color. What do we have in sine omega t? First of all, sine omega t here is 1 sine omega t. So it's minus omega square a times cosine phi. Okay, that's the first term. And what's the second term? Cosine omega t, sine omega t. So it's here. Here is another one. So we have b over m and omega a. And sine omega t here is a sine phi. Okay, any more for sine omega t, k over n, sine omega t. Oh, we have last one. It's k over m plus k over m a cosine phi. I think that's all we have. Okay, and okay, what's in cosine omega t? Okay, cosine omega t. Let's see. First term, yeah, we have 1 here, so it's omega minus omega square a times negative sine. So it's here. It's omega square a with a sine here. That's a cosine omega t. Okay, what else? Cosine omega t. So it's b over m plus b over n. That's the second term. It's here. B over m omega a and cosine phi. Yeah. And the last term. Do we have last term? Do we have less cosine omega t? Oh, we have this one. Oh, we have many terms in cosine omega t. Really? Okay, so it's minus mka cosine omega t. It's sine phi. Okay. Okay, so that's the equation we have. So first of all, let me check. Do I did the calculation correct? At this point. Okay, let me see. Let me do a check. Do we have the correct one? Oh, yes. Looks like a very complicated term. A cosine phi. Okay. So okay. Okay, so we have this term times sine t and this term times cosine omega t equal to cosine omega t. And let's give you the equation, because the right hand side only have cosine function, so you only have cosine omega t this function. So that means the coefficient before the sine omega t must be equal to 0. Okay, so we have minus omega square a cosine phi plus mb omega a sine phi plus k over m a cosine phi is equal to 0. Okay, that's the first equation, right? And okay, we saw the second, the right hand side only have if f0 over m times cosine omega t. So that means in the left hand side, and this coefficient in front of the cosine omega t must be equal to f0 over m. Okay, that's the second equation you have. Second, plus b over m omega a cosine phi and minus k over m a sine phi is equal to f0 over m. Okay, that's the equation. we will have, and we find everything there, or they all have the A, so we can cancel this first. Cancel this first, cancel this first, cancel this first, cancel this first, cancel this first. And then we do a little substitution. Okay, like in the damp oscillation, okay, the same thing. We let the omega 0 natural frequency square is k over m. And tau one reciprocal relaxation time is also equal to b over m. Okay, and then we will have the new formulation, and it looks much more nice. Okay, in my point of view, it is more nice. So we will have, okay, let's see, minus a, so we have omega 0 square minus applied frequency square and cosine phi plus tau, yeah, omega over tau sine phi equal to 0. Oh, okay, that's the first one. I think I got it right. And the second one is omega square minus omega 0 square. Oh, oh, okay. Omega 0 square, 0 square. I'm not sure. You're right. Oh, okay. The other is omega square minus omega 0 square sine phi. And plus tau over omega cosine phi is equal to z. Oh, no, not 0. F0 over m. Okay, for this equation, so, okay, we have two, finally reach these two equations. This is 1 and this is 2. Okay, from 1, we can get the tangent phi. Okay, from 1, we can get the tangent phi. Okay, you divide this by cosine, divide it by cosine, we will get tangent, we'll have tangent of tangent phi. Okay, tangent phi is just equal to, yeah, it become reverse, omega, applied frequency square, and minus natural frequency square, and divided by applied frequency divided by relaxation time, divided by relaxation time tau. Okay, and okay, so omega, and this what this tell you? This tell you your applied frequency. When you apply frequency, your applied frequency is not equal to your natural frequency. Natural frequency. Your system, you will have a leg. You will have a leg. You will have a leg, phase leg. Okay, phase leg. Or call phase constant, but you won't give it a meaning. It's called phase leg. Okay, that means your applied frequency and your natural frequency of system is not the same pace. That's why you have a lag when you apply the frequency of oscillating force into a system. It's not it. You can think about it. It cannot respond as it cannot respond immediately after you input oscillating after you apply oscillating force into your system. Once your applied frequency is not equal to your natural frequency of the system, you will have a lag. You have phase lag. Okay, that means the system will not respond immediately. Okay, that's why you have a lag. Okay, that's one of the first thing this equation tell you. Okay, applied frequency is not equal to natural frequency. You will have a lag. Your applied force the system cannot respond to your applied force immediately. Okay, that's the first thing you think. Okay, okay, so that's a one object we have reached. Okay, don't forget our object. The object is to obtain phase constant, right? Obtain phase constant, and the other thing, yeah, what's the amplitude function? That's the most important part in the force oscillation. What's the amplitude function? Okay, so how can we solve the amplitude function? Okay, let me think. Let me treat. Okay, from 2, what can we do from 2? So the amplitude must be from 2. Okay, from 2. Oh, so I divided the square out. Sorry, I cannot divide the A. Sorry, I cannot divide the A here. Yeah, in equation 1, I can divide it A, but equation 2, I cannot divide it A. Okay, because the right hand side, there is no A right hand side, so that I cannot divide it by A. Yeah, this is A we are trying to solve. Okay, but divide by this is not trying to solve. This is A. Okay, this is a A here. This is a A here. Okay, so this is a A. Okay, so we will have the so after all. Okay. So we will have A here. So sorry, we have A sine A sine phi, A cosine phi. Okay, A sine phi, A cosine phi, A sine phi, A cosine phi. Okay, and then we will get what is A. We can using 2, we can solve the A. So what is the A? A is equal to, yeah, don't think it's too hard. Okay, it's F0 divided by M, and it's omega squared minus omega 0 squared A sine phi. Oh, sorry, sine phi. Sine phi plus omega over tau cosine phi. Okay, so this is the most important conclusion in this part, but most of the time we don't want to phi here. We have to replace these two terms. We replace sine phi and cosine phi. Replace sine phi and cosine phi. So how to replace sine phi and cosine phi? Yeah, that we will use the tangent phi here. Tangent phi tell you this. So what's its meaning? If tangent phi is this, it tell you the sine phi and cosine phi. How does this happen? Okay, so actually it's also the I think high school mathematics. Okay, if this is the phi, if this is phi, okay, we have tangent phi is equal to this. That means tangent phi is here. Yeah, that's tangent phi. That's tangent phi. Okay, so you have these two information. So what's this side? This side is just equal to square root of these two lengths square add together plus omega over tau square. Omega over tau square. Okay. Omega over tau square. So, and then you can get the sine phi and cosine phi. Okay. Yeah. Check yourself because it's just the algebra work. Yeah, it's kind of, it's not really complicated, but it looks very complicated, but actually not complicated. So try this yourself. It's just the tangent phi is this one, so you can get the sine phi and cosine phi. Yeah, so if we replace sine phi and cosine phi, the final result is, okay, we result very famous conclusion. Your amplitude looks like this. Yeah, it looks like this: omega square minus omega 0 square, and plus. So here we might need to be careful. Tau over omega square. Sorry, this is tau omega. This is omega over tau square. And that's a very famous conclusion. We only find, we use lots of mathematical work. We find the A amplitude. What is this most important conclusion of this amplitude? So let's tell you, in forced oscillation, your amplitude is a function of omega. And what is omega? Don't forget, what's omega? Is your applied frequency. Your applied frequency. Yeah, it's very intuitive. You force the system to oscillate. You apply an oscillating force, and you apply a frequency into a system. So that's why your amplitude, your response of the system, it must be a function of omega. Okay, must be function of your applied frequency. It's very intuitively. But there's the only question: what happens when I keep increasing the applied frequency? What will happen? Will we increase or we decrease? Yeah, I think that's the thing we have to discuss in the next video. Okay, this video just tell you, in forced oscillation, your amplitude is a function of omega and function of your applied frequency. And in damped oscillation, I say the damped oscillation, your amplitude is a function of time. Okay, it's a times exponential decay function. That's in damped oscillation. But right now, in forced oscillation, your amplitude is a function of your applied frequency. And what the amplitude will change if you keep adding the keep increasing your applied frequency, what will happen? Yeah, that's very interesting, and that's a very interesting part in the enforced oscillation system. Okay, so in this video, I just show you the kind of mathematical work for the forced oscillation. I just want to know where this formula comes from, where this famous formula comes from. Yeah, just the mathematical work. Okay, they show the detail. So okay, so this video is kind of so long. I just start a video here. I'll keep discussing the forced oscillation in the next video. And see you in next video. Okay, bye bye. Bye bye. Okay.